Okay, should we start? So, good morning everyone. So, today the topic is semiclassical scattering. You already had yesterday a topic on semiclassical approaches. Yesterday was the discussion most concentrated at high energy. And at this high energies, we can make the so-called iconal approximation, for example. So to make, to assume that the trajectories of the projectile, of the constituents of the projectile follow some straight lines, and this produces a large simplification of the formalisms. So out of that, it was possible to calculate a number of observables that Jeff was describing yesterday. Momentum distributions, so first the S matrix and different diffraction, stripping, breakout, different components of the cross-section. Today we have a related topic. It's on semi-classical calculation, but it will be more focused on Coulomb excitation. So we cannot make the assumption of straight line trajectories. But we can make different assumptions of our trajectories, as we will see right now. So let me go from the outline. So just first of all, let's try to make an idea on how good would be a classical or semi-classical description. So imagine that we try to make a classical description of our nucleons inside the nucleus. So these are rough numbers that give us an idea of the magnitudes that we are dealing with. So the size of the nucleus is something of a few Fermi. The energy of a nucleon inside a nucleus is something of a few tens of MeV. This is a typical kinetic energy of this nucleon. And this corresponds to this approximate fraction of with respect to the speed of light. So if we calculate the characteristic wavelength of this particle moving inside this nucleus with this velocity, we get something of the order of 1 Fermi. So the wavelength is something comparable to the size of the nucleus. So clearly we cannot make a description of these nucleons in terms of classical particles moving inside. So quantum effects cannot be ignored as far as the description of the structure of this nucleus concerns. However, if we consider in a reaction process the motion of this projectile or target relative to each other, so this is again the wavelength of different particles, or including the photon, at different energies. So you see that, for example, in the case of oxygen system, for example, of 100 MeV, we have something that is very small, 0.11 is a Fermi, that compare to the typical distance that this particle will travel in the proximity of the target is small. So we can imagine the wave describing this particle as a small wave packet. And so we can think on these wave packets as a classical, following some classical equation of motion. So even if we cannot make a classical approximation for the particles inside the nucleus, we can, in some situations, so when this lambda is small, we can maybe approximate the relative motion by some classical trajectory. But keeping in mind that what we are describing is the motion of a wave packet that is small. The size of this packet is small compared to the characteristic distance in which this process takes place, which are maybe a few tens of Fermi. So we can distinguish between what would be pure classical scattering, which consists of classical particles moving along some classical trajectories, and this will require something of this kind, so the wavelength should be much smaller than the size of for example, the nucleus in this case. So this condition is very difficult to fulfill in practice in nuclear physics. Sometimes, in specific cases, it makes some sense, but not in general. And most commonly, we will have what is called semi-classical description of the process. that is to say, this corresponds to quantum particles moving along some classical trajectories. And this is essentially what Jeff was describing yesterday. So in order to have a defined, so typically we want to solve some equation of motion to obtain some trajectory. So in order to be able to do that, we have to assume also that this trajectory is not much affected, this classical trajectory is not much influenced by the internal excitations of the projectile. So remember when we discussed about inelastic scattering, inelastic scattering means that we have some energy that is transferred from the relative motion to the internal motion. This is an excitation process. This energy doesn't come from free, this excitation energy, this comes from the kinetic energy. So this means that we are changing the velocity, the kinetic energy of the relative motion, so we are making some distortion of the trajectory, thinking on this classical trajectory. So if this effect is very large, our classical trajectory will not make much sense. It will be very much distorted by this internal motion. So clearly we need an additional constraint. That is that this is the energy that is transferred to the, for example, to the projectile must be small compared to the total kinetic energy. So that we don't have a trajectory that is disturbed by these internal motions. And also the angular momentum, when we produce an excitation, we are changing typically the angular momentum, the spin of the nucleus. And again, this angular momentum comes from the orbital angular momentum, the relative orbital angular momentum. So we have had, in general, also this condition in order we can define a meaningful classical trajectory, characterized maybe by some velocity and some equation of motion that can be solved with some classical equations. Okay, so these are our constraints to be able to apply this semi-classical picture. So imagine, for example, so we have two problems. We have to solve now two problems: the problem of the classical trajectory, that is a classical problem, and then the quantum mechanical problem. So let's start from the classical problem. So there are many ways of describing a classical trajectory. So a possible way is instead in terms of these polar variables. So imagine, for example, this Coulomb problem with some charged particle. We have a projectile with some incident impact parameter, some classical impact parameter, and the equation of the trajectory is the equation that gives me the value of the modulus of this vector, the distance between the projectile and the target, and also this angle, phi or phi or whatever, as a function of time, for example. Or we can get in a parametrized form the trajectory, so r in terms of psi or the opposite. So we can choose the time as our parameter and describe how these two variables change in time, or we can write one in terms of the other. This is how one typically expresses the classical trajectory. So the equation of motions, you studied this probably many years ago in I don't know, in classical mechanics at least. So it's obtained by a conservation of the two quantities that are constant of motions in this case. This is the energy. The energy must be conserved. So expressed in terms of these variables, we have this kinetic energy plus the potential energy between them, and this must be equal to the kinetic energy at infinity. So this V naught is the incident velocity when they are very far apart, so they still don't feel the potential. And another equation comes from the conservation of angular momentum. So the angular momentum that is given here is expressed in terms of this derivative of phi, and this is the value that we obtain again from the initial conditions. So this is the impact parameter, the reduced mass between the projectile and target, and the incident velocity. Okay, so this is a classical problem. You have two equations. Once we fix the impact parameter, so we are fixing the angular momentum and the energy, the velocity energy, we can solve this equation for r or for phi, for both of them. So this is a parameterized form of the trajectory. If we eliminate the time variable, so many times we want to have, it's useful to have a parameterized form of the trajectory, an implicit form of the trajectory. So this is the general equation. So you have here the potential. You can define also an effective potential that is obtained adding to the normal potential, the centrifugal term, and define an effective potential that can be more easily written in terms of the impact parameter. And so, well, this provides us with the equation of motion if we are able to solve this analytically in some cases, but in general it has to be done numerically. Also, we will introduce the concept that we are going to use a couple of times of turning point. So the turning point, remember, is the distance of closest approach in the classical collision. So going back to this picture, so this is the turning point in this trajectory. So it's the distance at which the modulus of this vector is minimum. So this is obtained just by imposing this condition. At that point, so the distance is becoming smaller and smaller. At some point, it will reach the minimum value, and then we will start to increase because the nuclei will separate from each other. So there is clearly a minimum at this distance with respect to time, so can be obtained from this equation. This is just obtained from here by removing this term. So formally, we can integrate this equation from this turning point distance to an arbitrary point to get the equation of this phi as a function again of the total energy or impact parameter. So this integrated in some way provides us with this classical trajectory. We will not say more about classical trajectories. Afterwards, we will refer to the specific case of the Coulomb potential, and we will write down the equations of this trajectory, but I will concentrate now on the motion of the quantum mechanical dynamics of the projectile or target. So remember this slide from our previous days. So we have a Hamiltonian that contains the kinetic energy between the projectile and target. Now we are thinking on the projectile. So today I will think of the projectile as the nucleus being excited. It could be, of course, the target, or it could be both of them. So just to fix ideas, to simplify our notation, let's think on the projectile as the system that becomes excited, that might excite during the collision. So now our Hamiltonian contains three terms. Remember, we have the kinetic energy, the internal Hamiltonian of this projectile that we want to treat quantum mechanically. We cannot make classical approximations. This variable here corresponds, remember, to the degrees of freedom of this projectile, and some interaction potential between them that will depend on, in general, of these internal degrees of freedom. So we can have excitations of the projectile, right? So this is the same that we have. And the internal Hamiltonian can be solved to obtain some energies, the energy spectrum of this projectile, and the corresponding energies. Have changed slightly the notation with respect to the other day, so I think this slide is useful to define our notation today. It's similar, but not exactly the same. So the projectile-target interaction many times can be separated in two terms. So there is one part of this interaction that will not produce excitations of the projectile, but will be important to define this classical trajectory. So thinking, for example, on the Coulomb interaction, we have always the central, the monopole Coulomb interaction, the product of the charges divided by the distance times E squared, whatever. So this term will not be able to produce excitation. It does not depend on the coordinates, on the internal coordinates of the projectile. it just determines the motion of this projectile. So it is convenient to separate this from the full interaction. This will be the part of the interaction that we will use to define our classical trajectory. So we follow now. We have the classical trajectory. This R is a function of time or a function of the angle, of the final angle, the scattering angle. So many times we will write this R as a function of theta, as a function of t, to remind ourselves that this corresponds to some trajectory that depends on time. So now we want to follow the time evolution of the projectile. So we sit in the frame, the reference frame of this projectile, and we try to get the evolution of the wave function of this projectile as a function of time. So we can think, if we sit down in this projectile, eventually we see the target, like a comet passing nearby. So this will produce like a time-dependent potential between them. For some time, we will feel the distortion coming from this target, coming close to us, and then flying away. So this can be interpreted from the point of view of this projectile as a time-dependent potential. So the interaction between projectile and target here is something that depends on the trajectory and then depends on time. So this is like a external perturbation on our projectile. Our projectile is initially in the ground state, and now due to this target passing nearby, there is some perturbation, this V coupling, that is the part that we have separated from the interaction, and this will eventually produce excitations of the projectile. So this is the equation of motion, and now we have to use of course, the quantum mechanical equation of motion, because we are describing the excitation of the projectile, the dynamics of the projectile, that we agreed that has to be done in a quantum mechanical approach. Okay? Remember also that in our coupled channel discussion and so on, we all the time used this time-independent picture. Here it's more convenient to start from the time-dependent Schrödinger equation, because we have the time dependence here, so we cannot separate the time-dependent part so easily as we did in the coupled channels framework. Now we have the explicit time dependence on the potential. So this equation has to be solved with some boundary condition, as always. So our boundary condition is that at minus infinity with t, so this corresponds to the time with t is minus infinity, so when they are very far apart, the projectile is, for example, in the ground state, that we denote like this. Okay, so this is a natural initial condition. It's in the ground state, suddenly the target comes close to us and produces some perturbation, and eventually may excite this projectile to any possible excited state, and then flies apart. So we are interested in knowing what is the probability of populating the different states of the projectile. This is our goal. So let's go on. So the idea, and this is similar, this is a coupled channels version for the semiclassical problem. So remember that the idea of the coupled channels method was to expand the wave function in terms of the eigenstates of the projectile, target, or both of them. This was the idea of the coupled channels method. Here it's the same thing, but we have to keep also the time-dependent part. So we have some coefficients that may depend on time, but also we depend on the angle. And this can be thought as actually one equation for each different impact parameter. So we consider that the projectile and target collide with different impact parameters. For each one of them, we have a trajectory. For each impact parameter, we have a trajectory. And this trajectory can be characterized, so in some books, instead of theta, you have here the impact parameter b, but there is a unique connection in classical mechanics between the impact parameters and the angle. So we can identify the trajectory by either the impact parameter or the angle, the scattering angle. One impact parameter will give rise to one scattering angle. Okay? The opposite is not always true. Let's do it this way. So our initial condition that we have written before, so if we agreed that n equals 0 corresponds to the ground state, so in this expansion we have the internal state of the projectile, so we assume that at minus infinity the system is in the ground state, so this means that only one of these coefficients is different from 0. Our initial condition. So at minus infinity, so our initial state is not t equals 0, it's t equals 0 is defined here as the point of, as the turning point, actually. The turning point. So our initial condition will be at minus infinity. The projectile comes from minus infinity, collides with the target, and evolves in time to plus infinity. So always our initial conditions will be written in terms of this minus infinity. So the only coefficient that is different from 0 is actually 1, is the one that corresponds to the ground state. So now we plug this expansion into our Schrödinger equation that we have written in the previous slide, and we get a system of coupled equations, so similar to the system of coupled equations that we had for the quantum mechanical problem. These coupled equations, so the unknowns here, we know the internal states of the projectile. We have solved this problem already. So the unknowns here are these coefficients. So we have these coefficients here, dependent on the theta, on the scattering angle, and on time. And this is the time evolution of these coefficients. And we get here V and M that are written explicitly here, that are just our famous coupling potentials that we discussed at length in the last week on Monday. So again, our basic ingredient for the calculations are these coupling potentials, these transition potentials. So the strength of this coupling potential will tell us how important will be the population of the different states of the system. So if someone has a code to solve that, then this is what we have to provide in some way in the input by specifying what is our coupling interaction and, of course, what is the model that we use to describe the projectile. So far, we have not specified any model, but we could use the same models that we discussed on Friday, on Monday. So the cluster model, collective model, so any of the models that we have used can be used to describe this internal states. Okay? So probably the beautiful thing of this theory, one of the things that, one of the possible advantages is that the equations are probably more transparent to us because it is easier for us to think on some classical trajectories. We can have a picture in mind of what is going on rather than thinking on some complicated wave packet or wave function or some plane wave that scatters and produces some outgoing waves that eventually may interfere between them and produce complicated phenomena oscillations. Of course, this is a more accurate description, but whenever this approximation is accurate, is appropriate, it provides a very clear, very transparent picture of the reaction. So these kind of theories are useful not because they can provide us with simpler calculations, but because we can give us maybe a simpler interpretation of the reaction. Okay, so imagine that we have already solved the system of coupled equations. So now we have these quantities, this C. So we defined what is called the excitation probability, excitation probability as the square of this factor for t equal infinity. So this C factors, remember, depend on time. So it gives us at each time position, it gives us what is the population of the different states. So we can define some probabilities and excitation probability for each instant. So we can follow like making different pictures, making a movie of the projectile. At this, we take a picture as an instant. At this instant, we'll have a distribution of population of different states. We can obtain this information once we have solved the couple equations, just from the square of these probabilities. But remember, for a scattering problem, the relevant quantity are the amplitudes, the probabilities of cross-section at large distances, because our detectors are at infinity in the scale of the distances that we are dealing with. So we have to look at the value of these coefficients at very large distances. So this is the excitation probability, and the cross-section will be obtained as this excitation probability multiplied by the classical trajectory, by the classical cross-section, sorry. So this part gives me the probability of classically following a specific trajectory, and this gives me a probability of, in this classical trajectory, what is the probability of exciting some specific level. So remember that in this approach, the calculation is done for each angle, for each impact parameter. So for each impact parameter, we follow the classical trajectory and we calculate the probability of producing some excitation to some level n along this classical trajectory. This is the interpretation of this expression. And remember also that we had some, in the quantum mechanical approach, we had an S matrix, a dimensionless quantity or dimensionless matrix that was associated with the probability, so the square of this matrix associated with the probability of ending in some specific state of configuration. So this is what Jeff yesterday referred as survival probability, survival in some specific state. So in the classical language, in the classical picture, these C coefficients play the same role. This give us the probability of populating some state. So this condition here is similar to the condition that we wrote for the unitarity of the S matrix that was related to the conservation of flux. So at any time t, the sum of this square of this coefficient should add to 1. So this means that the total flux will be distributed between the different states, but the total flux must be conserved. This is what this condition means. Of course, here we are assuming that we don't have, for example, imaginary potential. So we are thinking on some classical trajectory described as a real potential. So there is no chance for flux going to this Q space, to this complicated space that would describe other processes that are not taken into account here. So this is not considered here, so we can strictly write this. There is a way, we are not going to enter into this discussion, but there is a way of taking into account these other channels. So imagine that a classical trajectory passes very close to the target, and this trajectory might produce some process that is not describing our simple model, not a simple excitation. So the system, for example, might just fuse with the target. So a projectile of one kind could just produce a compound nucleus, and this clearly will not be describing this framework. So a possible way of taking this into account is introducing a sort of damping factor, so that will appear here multiplying this expression, that is obtained as an exponential of some imaginary potential. So we can introduce also some imaginary potential here to account for this absorption related to any other channels that are not included explicitly. So if someone, we will not discuss this anymore, but if someone is interested in this particular aspect, I can recommend a couple of references where they discuss this in detail. Okay? So for us, this condition will be also always fulfilled. Okay. I don't know why we are missing part of the slides here, so I don't know if someone can help with this one. So first order perturbation solution. The solution of the coupled channels equation, even in the classical picture is involved because we have to solve all these couple equations for each impact parameter. So we have to solve many couple channel equations. This is similar. You can think always on the connection between the impact parameters and the angular momentum that was yesterday explained by Jeff. So in our couple channels calculation, remember that we obtain solutions characterized by total angular momentum J. And when you are running Fresco, you get in general a huge output because for each total angular momentum, the code will solve the couple equations and will give us some S matrices and some information. And this is done independently for each total J. So in some of your calculations yesterday, you had to include like 100 or 500 partial waves. Remember, for the lithium-7 case or oxygen-16, you have to put many partial waves. So this means solving many systems of couple equations. So here, the problem is slightly simpler, but still we have to solve for each trajectory, for each impact parameter, we have to solve a system of couple equations. If we have many states include this is still a complicated problem. So in the quantum mechanical picture, we have a useful tool that was the DWBA approximation. So the Bohr approximation was equivalent to treating the part of the interaction in first order perturbation. So we solved the some unperturbed equation to obtain some optical potential, and then on top of this we include in first order the remaining part of the interaction, producing some excitation. And the idea there was that the main part of the interaction was already included in our central potential, and then the part of the interaction producing, for example, excitations of the projectile gives a small contribution, so it could be treated perturbative. Here we can use the same idea. So imagine that this VNN is a short notation for these coupling potentials. So imagine that in this equation, these VNN are small quantities, so they are weakly coupled between them. We have very small probability of getting out of this elastic channel. So we start in the elastic channel, in the ground state of the system, and there is very small probability of exciting the system. So this means that the coefficient C0 that corresponds to the ground state will be close to 1. When we solve the couple equation, we will get a value slightly smaller than 1, but close to 1. And the other coefficients will be very small. This is our approximation here. So I write here this small in quotes because in practice one should find a more formal definition what a small means, but we will be happy here just to say that these coupling potentials have a small effect on the couple equation, and so we have this situation. So these are our starting couple equations, and in principle we have to couple for each state has to be coupled to all possible states, including the ground state. But if we think on some specific excited state, all these coefficients we are assuming that are small, and these coefficients, the only one that is significant is the C0. So in this sum, we neglect all the coefficients except the one that corresponds to the ground state, because the rest, the remaining, are small by assumption. So we simplify this sum by one term, that is this one with the C0. And actually, since we have agreed that this C0 is close to 1, we just replace it by 1. So we eliminate all the unknowns in this right-hand side of the equation. We have only to solve this time-dependent equation, but this can be done immediately because there are no other unknowns in the right-hand side. So by integrating this equation between minus infinity and plus infinity, we get the integral form of this coefficient. And of course, as a result of this calculation, we should get that this C fulfills this condition. If we get that this C is close to 1, then clearly the assumption that we have done at the beginning are not correct, and we should solve the full system of couple equations. So it's a self-consistency check. We have to make sure that these C are small quantities. Okay? Well, so let me introduce an important parameter that appears in semiclassical scattering, and in particular in the case of Coulomb excitation, but before introducing it in the case of Coulomb, so let me give a more general definition. This parameter is called the adiabaticity parameter. So let's define a characteristic excitation time. So the system, the projectile in our case, has a characteristic time to go from the ground state to some excited state, En. So this excitation time, this characteristic excitation time, this gives us an idea on how fast the projectile dynamics evolves in time. How fast it changes its internal state. So we will call this excitation time. So we define the adiabaticity parameter as a ratio. I write here the first time this superscript to distinguish it from the internal coordinates that sometimes we have defined with the same letter, but I think that will not create confusion. So later on I will just remove this R. So this adiabaticity parameter in general is defined as a ratio between a collision time and the excitation time that we have defined before. So the collision time, loosely speaking, is the time that during which the projectile is close to the target. So the time during which they feel their mutual interaction. And this will depend, of course, on the range, for example, of the potential. This will depend on the kinetic energy. If the collision is very fast, then the collision time will be smaller. We have a very low energy reaction, then it will be a gentle process in which they get closer, closer and closer, and so the collision time will be large. So we will give a more definite expression for this, but so far it will be enough to define this in this intuitive way. So replacing here our definition for the excitation time, we get this expression. So this adiabaticity parameter is a dimensionless quantity defined by this. And if you look at again the first order expression that we have just obtained, this quantity appears in this exponential. So in this exponential is multiplied by time. So, but in principle, this integral goes from minus infinity to plus infinity. But this interaction depends on time. So this interaction will be only important for some distances, so for a range of distances, or it means for only some part of the trajectory. At minus infinity or plus infinity, this interaction will be zero, the interaction between them. So clearly there is only one finite range of time, or finite distance at which this V is effective. So we can replace here the limit by some collision time. So what I try to express is that in this exponential, this t will go from maybe minus t collision to, or 1/2 of t collision to 1/2 of t collision. So this t is constrained by the range of time for which this v is important. Okay? So let's consider two very extreme limits, and the reality will be somewhere in between of these limits. So consider a situation in which this ratio, this adiabaticity parameter, is very small. So this means that the argument of this exponential is small. So this collision time is small, or we have a very fast collision, in other words. So clearly we need to have one of these two situations. Either for this parameter to be small, we need to have a small collision time, t small. If the collision time is small, this is a fast collision, so this occurs at high energies. So small adiabaticity parameters correspond to fast collisions, or also we could have very small excitation energies, such that this ratio is small. So either of these two conditions need to be fulfilled in order that we have this situation. This is called the sudden limit. This sudden limit corresponds, remember, to these fast collisions. And the other limit is the adiabatic limit, in the same way that was introduced yesterday by Jeff. That corresponds to the opposite situation. That is, in order for this ratio to be large, we need to have very large excitation energies, or we need to have a very small, a very large collision time. So if the collision time is very large, this corresponds to a slow collision, slow in the thinking, in the motion, in the relative motion between the projectile and the target. Now, in this particular case, if this argument is very large, this means that this exponential will have many oscillations within the range for which we are making the integral, so for the collision time. So this will have oscillation, and these oscillations, when we make this integral, will tend to cancel the integral. Remember that when we have some imaginary exponential and in one integral, we have many oscillations inside this typically will cancel the integral, because we will have positive, negative contribution that cancel each other. So in this particular case, the probability of this coefficient will be small in general, and the probability that the square of this coefficient will be small. So for situations for which this adiabaticity parameter is large, we typically can apply this perturbation theory, because the coefficient is small. Also, from the same arguments, the value for which this integral is a maximum will correspond to situations in which the argument of this exponential is close to 1, or the order of 1, sorry. So there is a range of excitation energies for one given incident energy that produces this adiabaticity parameter of the order of 1. So this will produce the maximum excitation energy. So this is the optimal condition for the excitation. So this will correspond, for example, for a fixed incident energy, this will correspond to some range of excitation energies. So we expect to have some excitation energy that are most populated for some specific reaction. Okay, so we have been considering only the first order perturbation theory. We are not giving many details of high order effects, but many times in literature people discuss about these high order effects, and it means different things in different contexts. So, for example, one of the meanings of these high order effects, imagine that we start from our interaction, and that this interaction can be separated. So before that, we did a separation between a potential that does not produce any excitation at all, and then the rest of the part. But this part that produces excitation maybe can be also separated into different pieces. So imagine, for example, that you have a multiple expansion of the potential. So you will have the dipole, the quadrupole, octupole. So you can separate this in different pieces, and maybe the dipole part will be the dominant one, and you want to trade this part correctly, means to solving the couple equations to all orders, but the remaining part, these high order terms, might be treated by perturbation theory. So now the idea is, so you see we have the dependence on the internal coordinates in both the V0 and the V1. So there's so the idea is to make an expansion of the coefficients of this kind, such that this C0 corresponds to the solution in the situation in which we neglect completely this term here, assuming that this term is small. So we can solve exactly the couple equations, but only for this V0. This is the part that is more important, and maybe this part is simpler to trade. So we get an exact solution. So this zero order solution is an exact solution for the V naught. Okay? And then we can use this solution and to put it into the full system of couple equations to obtain the C1. So this C1 will be a correction. So you can think this as a different correction. So you expect that each term here will be smaller and smaller. So this C1 will be a correction on the C0 that is obtained by this system of equations. So the C1 is determined by the C0s that we have obtained already, but also by the coupling to the C1s of the other states. So you have this complicated system of equations. There is an alternative way of writing this. It requires some derivation that we are not going to give, but I think that the final result has a very suggestive form. So I write only the final result. So the final result for this C1 that is equivalent to the one that I have just written is this. So these C0 are the ones that we have defined already. These are the solutions of the couple equations for the V0 part of the interaction. And here we have this C with twiddle, and this is also the solution with the V0 potential, but with a different boundary condition. So the C0, remember we start, our initial condition is a minus infinity, assuming that we start from a state 0. And so only the coefficient C0 is different from 0. This is the meaning of these two indexes. So one specifies the initial condition, and the other specifies the final state. And this C twiddle is defined in the same way, but now starting from plus infinity to a finite time. So we start from plus infinity with some initial state, that is the L state here, and then we go back in time, backward in time, and the system can eventually populate other states. But both coefficients are solutions of this system of equations. So the solution for the V0 with different boundary conditions. So I write the expression in this way because this is very similar to the result that in the quantum mechanical approach one obtains with this DWBA approximation, or more generally the coupled channels Bohr approximation. We haven't seen this in much detail, but I think, for example, in the DWBA approximation we have some, remember that we had some expression with some distorted wave here and here that were obtained with part of the interaction, and then we had the perturbation in between. This was the structure of the DWBA. We have some interaction that we were not describing, first order, and the distorted wave. So here we have the same expression. So the interpretation of this is that we start from the ground state, 0, the system evolves in time and eventually may populate a state M through the interaction V0. This is what this coefficient describes. Then, due to this perturbation, we can go from one state M to another state L, and then the system continues evolving in time with again with the V0, and this again may produce some changes of the projectile, but only due to this V0 interaction. So graphically, this corresponds to this situation. So imagine we are in the ground state initially, so the system is evolving with this V0 interaction. So this is a simple example in which the V0 does not depend on the internal coordinates. So it cannot produce excitation. So this is a generic excited state. At some point, the V1 acts on the projectile and produces maybe some excitation to one state N. So this is what produces the transition to 0 to N. So this produces some excitation. And then the system evolves in time with the V0 that cannot change again the state of the system. So here in red is the state that is populated at each instant. So in the final state we end up in this N state. So here the C0 describes the trajectory, essentially, the motion of the projectile, and the V1 describes the excitation to this state. This is the graphical interpretation of this expression, and this is, remember, very similar to the DWA expression. You have to think in that case, well, you don't have a time-dependent picture, and also this C would correspond to our distorted wave in the DWA method. Okay? Okay, so let's go to the Coulomb excitation. So one of the main applications of these semi-classical equations, approximations, are for the Coulomb excitation problem. So let me first define a few common variables and parameters that appear in the context of Coulomb excitation. So the A naught is the distance, half of the distance of closest approach in a head-on collision. In a head-on collision, remember, is a collision for zero impact parameter. So this is half of the distance of closest approach. This kappa here would correspond in the international units to the 1/4 pi epsilon 0, but in general we omit this in the expression, so I will omit in the subsequent expressions. Also, we could define a distance of closest approach for a finite impact parameter. So we have a finite impact parameter. The distance of closest approach will be larger, in general, because of the centrifugal barrier that will tend to keep the projectile and target apart. So this is the distance of closest approach for a specific scattering angle. And this quantity, 1/sin of theta over 2, appears many times. So one defines usually a quantity that is called the eccentricity of the orbit, of the classical orbit, to simplify this notation. Also, we have introduced the adiabaticity parameter in a general problem. In this case, the adiabaticity parameter for a head-on collision, so corresponds to theta equal pi, the head-on collision, so pi 180 degrees scattering angle. So this was the general definition, and a possible estimate, a definition of this collision time in this context is the time obtained as the distance, this half of the distance of closest approach, A, divided by the velocity of the projectile. So this is a common definition of this collision time. So this is the adiabaticity parameter for head-on collisions. Actually, many times we don't specify that it is for head-on collisions, so whenever we write the adiabaticity parameter without any additional specification, we are thinking always on this theta equal pi to 180 degrees. But more generally, one could introduce the adiabaticity parameter for each orbit, because the collision time, since this distance of closest approach depends on each trajectory, one could make a specific definition estimate of this adiabaticity parameter for each scattering angle. So when we write explicitly this theta, we will be thinking on some trajectory. When we don't write anything here, the argument, we will be thinking on head-on collision. Okay? So these are just some definitions that are useful for the context, a specific context of Coulomb excitation. The validity of the semi-classical approximation. So remember the definition of this Sommerfeld parameter that appears also in the quantum mechanical picture. So remember, for example, that our Coulomb functions f and g, remember from the first days, depend on this Sommerfeld parameter, on this eta parameter. It was defined in this way. This actually, in terms of the quantities that we have introduced so far, can be obtained as the ratio between this A naught, this half of the distance of closest approach, and this wavelength, the Broglie wavelength. So in order this picture makes sense, we have to assume that the wave packet that describes the projectile, the size of this wave packet has to be small compared to the characteristic distance that this projectile is traveling in the proximity of the target. So this distance, if we estimate this distance by this A naught, characteristic distance of this collision, then this ratio, so this gives us an interpretation of the Sommerfeld parameter. So this ratio should be small. So this is the condition that we are expressing here by words. So this ratio will be small, meaning that the Sommerfeld parameter has to be large in order this picture is valid. So this is a condition of the validity of the semiclassical approximation in the context of Coulomb scattering. Another interpretation for that is that if this lambda is small compared to this A naught, this means that there is a small penetration probability of the projectile in the region of the target. So A naught, remember, is half of the distance of closest approach. So if this ratio is small, then this means that we have a small probability. So it makes more sense to think of some classical Coulomb trajectory. If we have a large penetration probability, then the trajectory will be distorted by the Coulomb by the nuclear interaction, and so the approximation of these classical trajectories by Coulomb trajectories will not be valid. So we can give several interpretations of this. In addition to that, remember, we have to assume that in order we can solve our equation of trajectory independent of the rest of the potential, then we have to assume that the trajectory is not much affected by the energy transfer to the projectile or angular momentum transfer. And these two conditions that we already had at the beginning in the general case. So we have all these conditions that are necessary for the validity of the expression that we will show now. Okay? So in this specific case, remember, we have we can make a Coulomb multiple expansion of the Coulomb interaction, and we separate the monopole part, and the reason is that we will use this monopole part to calculate the trajectory, and then the different multiples of the Coulomb interaction. So this is the same expression that we had in the quantum mechanical description that we did in the previous days. So this V naught will determine the trajectory, but will not produce excitations of the projectile. Okay? And this V coupling will be the one responsible for possible excitations of the projectile. So remember also that at the beginning, in the coupled channels discussion, we had some generic states described by N, but in practice, it was useful to introduce explicitly the angular momentum, the spin of the projectile or target. Remember, we had this in the quantum mechanical description here. It is the same. We have some states, but in practice, it will be convenient to label these states by the spin. So, in this particular case, so this V naught that corresponds to the central Coulomb interaction, to the monopole Coulomb interaction, will be used, as we say, to obtain the trajectory for each scattering angle. So we have to solve this problem, but in the case of the Coulomb interaction, this trajectory can be obtained analytically. So there is an analytic form of the trajectory. There are several ways of writing this equation, but a usual and useful way is in terms of some dimensionless quantity, this omega here. So this is the description of the different magnitudes of describing the trajectory in terms of this omega, of this dimensionless quantity. So also, sometimes instead of using, for example, the distance between the projectile and target, one scales this by this A naught. So we have also some dimensionless quantities related to the distance. So we measure the distance in terms of the scale of this distance of closest approach, or half of the distance of closest approach. And the same for also for other variables. So we introduce dimensionless quantities to parameterize to describe the trajectory. So remember, now we want to apply the simplest approximation, that is the first order description of the Coulomb interaction. So this was our general expression. Remember that we have this situation. So in first order, and now we put it explicitly, we have something like this, with this exponential, this coupling potential. So now if we put explicitly the form of this coupling potential, so remember this was the matrix element of the interaction potential, the coupling potential between the internal states, and we have agreed that we are going to describe this internal states in terms of the spin and the projection of the spin. So we have this coupling potential written here. We can extract, this is an integral in time, we can extract from the integral everything that does not depend on the time, and the only thing that depends on time is actually the distance r. It depends on time because we have a time-dependent trajectory. So this distance is evolving in time, so we cannot just single it out from the integral. So, well, these integrals that appear here, these are the spherical harmonics. So these are actually analytical quantities that can be calculated or tabulated and can be implemented in some code. So many times one writes this integral in terms of this other integral. So these I are called the Coulomb integrals and are defined in this way. So here we have introduced this parametrized form of the equation. So we have replaced the time and the distance r by the dimensionless quantities that we have introduced before. So this looks like a very complicated object, but at the end these are analytical quantities that can be evaluated by some code or whatever, or we can find some analytical limits. So this part, we don't have to worry much about this because will be evaluated in some way. And this part here contains the information on the structure. So remember, the DWBA, this is equivalent to our DWBA approximation. In DWBA, we had something, some amplitude that was proportional also to these quantities. Remember, these are the reduced matrix elements of the electric multipole operator. Remember that? So we had exactly the same structure. Here, I have used also the Wigner-Eckart theorem. So remember that this was done to separate the dependence on the projection of the angular momentum. So at the end, the physical ingredient is again here. So we have exactly the same structure and the same physical ingredient. So in principle, by measuring, so the message here is again measuring Coulomb excitation, the excitation probability is related to the square of this quantity, and the square of this quantity is related to the square of this. That is related to the BE lambda, so to the electric transition probability for some multipolarity. So this is the same that we have in the DWBA approximation. This is a different way of getting this result within the semiclassical approximation. Okay? Well, the advantage of that, as I say, is that in the semiclassical approximation, well, we have to evaluate the DWBA amplitude, and this contains some distorted way that, so at the end, it has to be solved with some numerical procedure with Fresco, for example. Here, these quantities are tabulated, so we can get the actual numbers in a much more simpler way. So we have a more clear interpretation of what is going on in this case. Any question?
Initial approximation was the Cn is the very small
Yes.
compared to the C itself. And in this case, we use this further expansion with regard to T. Then we take the first part of Cn.
Yes.
To what extent is that's a second, so to what extent the first part of Cn is smaller compared to this?
Well, for example, it depends on all the pieces of this expression. It could be, so this could be large for different reasons. For example, if we have a very heavy target, we will have a strong excitation probability, so probability C will not be that small. So also is this reduced matrix element that gives an idea of the strength of this coupling. If this is large, this also might be not appropriate. Also depending on the angle. So here we have the adiabaticity parameter, this xi, and this epsilon, that remember is related to the eccentricity of the orbit, is related to the scattering angle. So in some combinations, for some combination of the scattering angle and excitation energies, also this could be large. So depends on the problem, but also depends on the kinematical conditions, depends on the angle, on the excitation energy. So summarizing, so this means that this approximation will be valid for some reaction only for some range of excitation energies and some range of scattering angles. So typically, we will see this now, this will be valid for small scattering angles, but will not be valid for larger scattering angles, because then this becomes larger. So we will see this in a moment. So let me show you also the expression of the excitation probability. The excitation probability is related to the square of the C's, these amplitudes. So in this first order approximation is given by this expression here. And so as we said, it will be proportional to the electric transition probability. And the cross section is, remember, is we have to obtain as a product of the classical, the elastic cross section, yes, classical differential cross section, that is the Coulomb differential cross section times this probability. So we get at the end an expression of this kind when this F is of course related to these quantities, and it's written down here. So this is the final expression for our differential equation. Again, this F can be a complicated object, but everything here is analytical. It depends only on the adiabaticity parameter that is related to the excitation energy. So it will be different for each final state, and depends only also on the scattering angle, this theta here, that appears also through the eccentricity parameter. So for each excitation energy, for each scattering angle, we can evaluate this analytically with some code, and then the rest of the part of the expression is analytical. So this is, I think, a beautiful result of some clear connection between some reaction observable, in this case the excitation cross-section, and some quantity, some structural quantity, that is the B lambda. So it's relatively easy to make estimates of the importance of Coulomb excitation just by starting with the known values of this B lambda and then calculating these kinematical factors. This is how this F function looks like. So we say it depends on two things. It depends on the scattering angle, and it depends on the adiabaticity parameter, Xc. This is for the case of E1 excitations, dipole excitations. So each line here, so the units are missing, but so this is the scattering angle, yeah, from 0 to 180. This is the value of this F, and each line here corresponds to a different adiabaticity parameter. The adiabaticity parameter that is related to the excitation energy and also to the incident energy, because we have in the definition the V, the velocity. So you can see, well, you can see many things, but the most important, this for small adiabaticity parameters, we start from this is eta equal, well, it starts at 0 actually, but at 0 it diverges. So for finite xi, we have a finite values here, and then as we increase this adiabaticity parameter, 0.2, 0.4, 0.5, and so on, the F function becomes smaller and smaller. So for example, imagine that we fix the incident energy, the velocity, so the adiabaticity parameter can be changed by increasing the excitation energy. So by what this is telling us that if we increase the excitation energy, the excitation probability will become smaller and smaller. This is already what we saw in in the discussion of the first order approximation, because we have this exponential that contains also this adiabaticity parameter in the argument. So for large adiabaticity parameters, we have oscillations in this exponential, this complex exponential that will tend to cancel the integral. So we conclude that in that case the excitation probability should be small. This is actually what we get when we evaluate explicitly this f function. So for very high excited states, independently of what we have here multiplying, the excitation probability will be small. So for any reaction, if we go to sufficiently high excited state, the cross section will be small. Okay, this is what one would expect. Yeah.
I don't understand why in spherical harmonics theta is equal to pi over 2.
This is just a definition. So you start from here. This is the integral. So you write you equal this equal to this. So this is just a constant that is chosen for convenience. It's not that we are fixing the angle to theta to pi half. It's just equating this to this. So this is just a definition of this integral. So this will be some constant factor that appears multiplying, and this factor turns out to be just this spherical harmonic. This is not related to any choice of the scattering angle. There is no approximation between here and here. So the product of these two things are just this integral, this analytic integral. Okay, so this is just to have a more beautiful, let's say, expression for the Coulomb integral. That is this one. So all the remaining factors appear in this spherical harmonic. This is just for convenience. We could put this into the definition of this Coulomb integral, so we would have some not so beautiful factors multiplying the integral. Okay. Also, another feature that we observe is that for a scattering angle, for a small angle, scattering angle, except for the first line that goes actually diverge. So for finite adiabaticity parameter, then the cross section at 0 degrees is 0. And this can be also understood from the fact that the adiabaticity parameter is actually a quantity that depends on the scattering angle. Remember that we did a general definition depending on the scattering angle. So for scattering angles tending to 0, we have that the adiabaticity parameter, if you go back to this expression, tends to infinity in principle in the equations. And again, we have the situation in which the probability goes to 0 because we have a very large adiabaticity parameter. So this would correspond to the adiabaticity parameter when we don't specify that for head-on collision. So this is the label here would be the adiabaticity parameter defined for this quantity. But in general, we have something that depends on the angle. So even for a fixed value of this adiabaticity parameter, that is each of these lines, then we have a dependence, different adiabaticity parameters depending on the angle. So this is the reason. Okay. Let me go further. So many times so what we have discussed is what is called the Alder and Winter theory of Coulomb excitation. After these two persons that develop in detail this theory, and they have many papers on that and a famous book on that. I will add afterwards a slide with some references that I forgot to include that might be useful for you. So the main reference here is probably the book of Alder and Winter. That is a nice reading with a lot of discussions and a lot of useful expressions of this kind. But let me almost finish by relating the Coulomb excitation to what is called the photoabsorption cross-section. So the photoabsorption cross-section is a process by which a nucleus, a composite nucleus, A, that is composed of B and C, dissociates due to the absorption of one photon. So we have a photon, imagine a process, we have a single photon that hits a nucleus and produces an excitation such that the system is broken up. So this is the process that we are describing. So this photo absorption, cross-section, this process, that is not the process that we are discussing. So here is a thing of this photon hitting a nucleus. This process has a cross-section for some multipolarity lambda that is also related to the B1 distribution. So we are thinking now on a process in which the system A breaks into two fragments. So we have here the continuous B1 distribution. Here I'm anticipating the discussion that I will give later on, but you can imagine that going from bound state to continuum state, you have to introduce some continuous distribution, and actually you have found this in the previous days, so you will probably not be strange with this kind of expression. So this is the expression of the photo absorption cross-section, and there is a derivation for that is not given here, so don't try to understand this expression according to what we have discussed. This E gamma here is the energy of the photon, and the rest are just some constant factors. So remember that we have that our cross-section is proportional. Sorry, yeah, is proportional to the B1 distribution. For systems that can break, so this cross-section becomes actually a double differential cross-section. So we go back now to our projectile target system. So this expression here is replaced by expression of this kind. So this is just the generalization of this expression for the case in which we are exciting to the continuous state. We are breaking the system. Okay, so this is just a generalization of this. This is essentially the same expression, but now we have, instead of this f, we have this function, this differential form of this function. So we have a continuous function on the energy and angle, but essentially everything is the same. So we have an expression here that is proportional to the B1 distribution, and you see that here the photo absorption cross-section is also proportional to the B1 distribution. So in principle, both processes, the Coulomb dissociation and the photo absorption processes, are proportional to the same quantity. So we can actually write our Coulomb dissociation probability cross-section in terms of this photo absorption cross-section. Just playing with the two expressions, we can write our Coulomb dissociation in terms of this expression. And the factor that we get when we play with these equations, so you can do this on your own to convince yourself. So this factor will contain, of course, these f functions that we have introduced and some other kinematical factors. So we put all the kinematical factors into this quantity. This quantity is usually called in literature the virtual photon number, or the number of equivalent photons, and the name comes from the fact that you can interpret our Coulomb dissociation process as an exchange of photons between the projectile and target. For each photon that is exchanged between them, due to this Coulomb interaction, we have a photoabsorption probability of this kind. So this is an estimate, or could be interpreted as the number of photons that are actually exchanged by the projectile and target. So this is called the number of virtual photons. So in one of the exercises this afternoon, you will get this number, not analytically with some code. So you will estimate the number of virtual photons that are exchanged. This number of virtual photons depends on the charge of the target. So if we have a heavier target, this goes as z squared. So we have more photons that are exchanged. So this cross-section will be larger. This is normal. So we have more photons, we have more chances to excite our system. But also depends on the other kinematical condition. For example, depends on the velocity, and then depends on the incident energy. Sorry, the incident energy appears here, but also appears here. So it is not obvious from this expression. If we increase the incident energy, will this become larger or smaller? So this is something that I leave as an open question, and this afternoon you will do the calculation and tell me the answer. If this number increases or decreases when we increase, for example, the excitation energy. The incident energy. Okay. So this in the case of, we are now applying the model to weakly bound systems. So assume a process that is dominated by Coulomb breakup. So our formalism is appropriate. Of course, we could have also nuclear excitation. We have seen examples of that in the coupled channel framework. But we will assume that we isolate some reaction, and within this reaction we concentrate on some kinematical conditions, maybe some angular range for which all the approximations that we have been obtaining, and in particular this first order approximation, is valid. So we try to search for kinematical conditions for which our expressions are appropriate. So remember that we have this connection between the Coulomb dissociation and the B1 distribution. So this depends on the angle and on the excitation energy. The Coulomb dissociation, the pure Coulomb dissociation, will be only valid for impact parameters that are not too small, because if we have a impact parameter that is 0, in general we will have nuclear effects going on, because the projectile and the target can come close to each other, and there will be in general some other processes. So it's very difficult to find in actual situations the pure Coulomb excitation in a reaction. So you have to concentrate in some angular region that corresponds to large impact parameters or small scattering angles. That is equivalent. So if we integrate this quantity in some region of scattering angles, so we make the integration up to one angle. I don't know if we have introduced also the grazing angle. I think that at some point we say something, maybe a couple of sentences about it. So the grazing angle corresponds to what is called a grazing collision. So it's a collision for which the impact parameter is of the order of the sum of the radii of the two nuclei. So they touch, but only gently, so they don't fuse with each other. So this is an estimate of the scattering angle beyond which we expect to have some other effects that are not purely Coulomb. So to be safe enough, we have to integrate this expression for scattering angles that are at least small than this these grazing angles, to make sure that we have a small scattering angle, large impact parameters, so distant collisions, so only Coulomb interaction, and the nuclear interaction is not playing a role in this, at least in this angular range. Of course, in a collision, a more head-on collision, we will have other processes and absorption of some other things. So we try to isolate some kinematical situation in which our expression is valid. So in this situation, this differential cross-section as a function, this Ex is the excitation energy. So this excitation differential cross-section as a function of the excitation energy integrated in this angular range, according to this expression, is proportional to the V1 distribution. So when making this integral in the angle, so we have the integral of this number of equivalent photons. So this can be also done analytically. So this is given by this number. So we have something, a cross-section, that is proportional to the V1 distribution. So by measuring this Coulomb dissociation cross-section, we can get information on the V1 distribution of the continuum. So the idea is that when we have a halo nucleus, or in general a weakly bound nucleus, this is a very weakly bound system, so the system will be easily polarized in the Coulomb field. So when we put this nucleus in some Coulomb field, for example, if we think of a neutron halo, then only the core will be distorted, so the system will be stretched, and eventually it may break up. So this means a large E1 response to the continuum. The system is polarized and can break up into, in this case, the neutron and the rest of the nucleus, the core. So we have a large E1 response to the continuum. So when we do a scattering of this nucleus with a heavy target, this provides us a source of a strong electric field that may produce this effect of distorting and eventually breaking the system. So doing an experiment of halo nucleus with a heavy target will produce a large cross-section due to this Coulomb excitation. So if we concentrate, according to the discussion that we have given in the previous slide, in a region for which we are sure that Coulomb dominates, so small scattering angles, then we can extract the B1 distribution from the cross-section, Coulomb dissociation cross-section, as a function of the excitation energy. Because these two quantities in this approximation are related to each other by this simple quantity. And this is actually, this has been the method used by in many papers that try to get this quantity from this cross-section. So this is something that is not only useful from, say, academic purposes, but is also used every day. And many physics letters papers have been produced using this this analysis. So you don't need to go to a very complicated calculation to get a useful analysis. So this is an example, and this is the example that you will do this afternoon. This will not give you probably a physics letters because it was already done by someone else, but maybe in future you apply the same technique to some other system. You can produce new results, but this afternoon we will be happy just to reproduce the results of this paper. This is a beautiful experiment, beryllium 11 breakup. So this is not a simple experiment because in order to obtain these quantities that we have been discussing, this energy distribution, so you need to measure in the final state. So you are breaking the beryllium 11, you have to measure the beryllium 10, but you have to measure also the neutron. So you need to measure the energy and the angle of the scattered neutron. And the reason is that if you want to construct this kind of spectra relative to that correspond to the relative energy between the neutron and the beryllium 10, so to obtain the excitation energy of the beryllium 11, then you need to get the two momenta, the two linear momenta. So energy and angle of each of the particles. For beryllium 10s it's not that difficult, but for neutrons it's really difficult because detection of neutrons, as you know, is not easy. So typically this is done with a small efficiency, and you have to be very smart to have enough statistics and so on. But in this case, you see that they managed to get these beautiful curves. So we concentrate on the lead target. This is carbon target. That is a different story. So we are interested in Coulomb excitation. So we look at this spectrum. This is for the energy. This relative energy is simply the energy between the neutron and the beryllium 10. So the total excitation energy will be this number plus the separation energy. So you have, in this case, to sum 0.5 MeV for the excitation energy with respect to the ground state. So 0 means here 0 relative energy between the neutron and core. This is just the breakup threshold. And this is the cross section. So here they put a constraint in the maximum angle to extract this angular distribution. In general, you have a double differential cross section with respect to excitation energy and with respect to angle. So we go now to this. This is the angular distribution with respect to the scattering angle. So you have to make an estimate of what is your grazing angle in order to make sure that you are observing only Coulomb excitation. So for example, if you cut at 6 degrees here and integrate the angular distribution, then you get this energy distribution. But if you want to make sure that you have only Coulomb, you could also put the cut before, maybe at 1.3 MeV, so this somewhere here. So you integrate only up to this angle and obtain, then you have, of course, less statistics because you have less counts, but this corresponds to this angular distribution. So the lines that you see here, and you will reproduce this afternoon, corresponds to the calculations with this equivalent photon method. So from these calculations, they try to infer the B1 distribution of this system. That is just proportional to this quantity. Okay? So I know that we We are coffee time, but I have only a couple of slides more, so maybe I finish here, and after the coffee, we will dedicate the session to the CDCC, to continue with your CDCC calculations, because maybe it's useful if you have some time to make questions on CDCC. So this is another example. This is for the case of lithium-11 or lead at Coulomb barrier energies. So the experiment here was at relatively high energy, 70 MeV per nucleus. This is a Coulomb barrier energies. So, and here you have a comparison. This is, you don't see here, this probability. So this is similar to what we have introduced as a probability. So this is defined as a ratio, essentially, between the lithium-9 fragments and the elastic fragments. So this is the ratio between the breakup and the elastic, as a function of the scattering angle, in this case in the laboratory system. So these are for two incident energies. So you have two lines here. The blue one, well, you have the experimental data, and you have the blue one is a full coupled channels calculation. This is for lithium-11 that is treated as a 3-body system, so this is a 4-body reaction calculation. So it's a very complicated problem from both, particularly from the quantum mechanical point of view. You want to make a few-body description of the projectile. So this is the blue line. And the red line is the semiclassical calculation obtained with this equivalent photon method. So remember, we say that we only rely, we only believe on this, we only trust on this approximation at a small scattering angle. But the meaning of a small or large scattering angles will depend also on the kinetic energy, on the velocity, because what matters is the ratio between the collision time and the excitation time, so the adiabaticity parameter. So in this particular case, you see that the two approaches coincide very well, agree very well with each other up to maybe 30 or 40 degrees. So this is not a small angle, as we saw before. And then they start to depart. So the red line does not agree with the data in this region, but this is not something that we don't expect, because we know that larger scattering angles, then maybe this approximation, first order approximation, is not valid, and we have other kinds of effects. So well, maybe I changed my mind, so we stop here, we make a break. I see your faces. I need also a coffee. And I think that in 10 more minutes after the coffee, I finish this, and you devote the rest of the session to CDCC. Okay? So